Hello and welcome to this SimScale webinar on cooling high power density data center hardware. My name is Dr. Nagman Khan. I will be your moderator today, and I'm delighted to welcome a very innovative engineering company, Submer, who are our guest presenters today, represented by Mr. Luis Castrillo, who is a thermal engineer. Welcome to Luis. And I'm also delighted to welcome my colleague, Victor, from the customer success team at SimScale. Why are we here and what do we do? Well, SimScale is empowering engineers to innovate faster by making high fidelity engineering simulation accessible from everywhere and at any scale. And we're going to hear how this has benefited Submer and how they've used and leveraged the engineering simulation platform to accomplish their goals and objectives. First, let's take a closer look at today's application. We're going to see a quick overview of the SimScale platform. That will be my colleague Victor. Then we're going to hear from Submer on how they leverage engineering simulation in the cloud to optimize cooling, high power density applications, including data centers and electronics cooling, and also by using CFD, multi-phase flows, and structural analysis. We'll then have a live Q&A with Submer and SimScale, and then we'll show you at the end how to quickly get started with SimScale and start simulating on your own. Now, do keep the questions coming. We have a questions panel on GoToWebinar, and we'll collate all the questions and take them at the end. I'd now like to hand over to my colleague, Victor, to show you a quick overview of the SimScale platform.
Thank you, Nagman. So, welcome everyone. Just to start off, a quick overview of the SimScale platform. So today here we'll be looking at the performance of this electronics cooling box. So if I just quickly hide this part here, we can see I've got an external case and then plenty of internal components with multiple CPUs, transistors, etc. Here, I'm looking at the overall workbench of SimScale. So this is where you'd be doing the majority of your work in the platform. And over here on the side, we see the simulation tree, which as I expand it here, this is where I'm going to input all the different parameters to my simulation. So I'm just going to quickly follow it top to bottom. First off, we would implement the geometry or choose which CAD I wanted to use for this particular simulation. I'll set up gravity vector, so letting the simulation know which direction buoyancy is going to take effect in. I'll choose the various materials in my system. So that's going to be what the gas is, in this case air, and the various solids that compose this piece. We have various inbuilt solids that you can lean in on from the material database. After that, I'd go through my boundary conditions, set up the ambient conditions, what's coming into the system, what's heading out, and finally, my power sources here. So basically how much each chip or electrical component is going to be generating in terms of heat. After that, I would just quickly set up the mesh. So this is basically like the resolution on your computer screen. We break down the problem into multiple small parts and solve fairly simple equations across those different parts to come up with a very complex picture in the end of the day. Once I've done all that, I can set up my run. And one of the interesting things about SimScale is since everything's done on the cloud, let's say, for example, I wanted to investigate this case at a multitude of different ambient conditions. I could quickly set up a run at, say, 15C, quickly change that, again, setting it maybe down to 10C. And both of these jobs, they're going to run in parallel on the cloud. So I'm not going to have to wait for each one to run in series. I can go get on with my day. It's not using my laptop. I'll come back, and once things are finished, I can post-process my results. So taking a quick peek at what we got here. Here we can see the results. So this is for the ambient conditions at 20 degrees. I can see, well, clearly I have a slightly hot spot towards this end of the casing and also over here. So I might want to investigate, hey, why is that? And what can I do in my design to improve it? So one thing I like to do is usually I'll make cutting planes. This is a really good way to get an idea of the overall flow. And I think that answers our question for this side quite quickly. So I can see here that while I've got quite a good amount of flow through the center here, through these channels, between these PCBs, see I've got quite a stagnation zone over here, which is going to be creating those higher temperatures. So one thing I might consider in the future for the design iterations would be to investigate whether maybe flipping this PCB over and having the electrical components over on this side with the higher wind velocities or air velocities would contribute more to cooling. Another way I like to visualize my results that I think is quite powerful and really indicative of the flow is through particle traces or streamlines, as you may know them. See basically little comets that follow the overall flow. I like to set up myself an animation. And again, I find this gives me a very intuitive idea of how exactly the flow is behaving. So here I can see as the particles come in, we've got a high velocity region again through these gaps, and we see again that stagnation, that slower particle velocity over on this end. Again, this gives me a good visualization that we've got a pretty good amount of flow coming in between these grills as well, which again is going to ease the overall cooling performance of this system. And with that really quick overview of the SimScale platform, I will hand over to my friend and our colleague from Submer, Luis.
So thank you, Victor, and Negman for your presentation. So welcome everyone to this webinar. Well, my name is Luis Castrillo, and I work as a thermal engineer in Submer. And I've been working here for over more than a year and a half, helping developing our immersion cooling products. And I would like to, well, just present myself. Most of my career is based on R&D projects, starting off in university with a Formula student team, being the head of cooling systems. Also working as a researcher in energy efficiency in the Polytechnic University of Catalonia. And now here in Submer, as I already mentioned, developing all these immersion cooling products along with our engineering team. And I'm also currently going through a PhD project with the company and also the university. So that's me. And I would like to talk a little bit about Submer. This company was founded in 2015 by Daniel Pope and Paul Weiss in Barcelona. Since then, we have grown to become an international company with a great reputation for providing the data center industry with innovative solutions to the cooling problems. Now we have over 85 employees worldwide, and we mainly focus on three main areas, which we call Submer Cools, Submer Scales, and Submer Labs, which I explain later on what this means. So Submer mission is to enable next generation cooling and automation for data and energy intense environments by using highly efficient and sustainable technologies. This mission still remains to this day as the main driver of the company, where the main goal is to help enabling data centers that make sense through products, APIs, processes, and installations that will move hyperscalers, colocation, and huge industries to new levels of efficiency and innovation. The main characteristics of smart data centers are mainly the ones we see here, that contributes to the ones that contributes to a data center being considered smart are some of these ones that we can see on the screen, which are sustainability, efficiency, and power density per square kilometer. And here's where I can remind you of the Submer Cools topic, which is everything related to immersion cooling, Submer Scales related to robotics in the data centers, and also Submer Labs, related to energy storage and research. So for today's presentation, we're going to focus on our immersion cooling solutions, which is where the company began. So we will specifically talk about our SmartPod and MicroPod solutions and how we use SimScale's technology to develop our immersion cooling systems. So here we have a very quick overview of all our current solutions, which range from SmartPod to the MicroPod to the MegaPod, and of course the Smart Coolant, which is the key character in all our solutions and the fluid that we use for cooling all the devices. So the SmartPod is our first immersion cooling device, and its heat dissipation can range up to 100 kilowatts at 40 Celsius degrees of water secondary cooling circuit. The main working of the SmartPod is submerging the IT hardware in our Smart Coolant solution, which is one-phase liquid. This one-phase liquid cools down the servers and maintain a proper temperature during its operating conditions. And this Smart Coolant is cooled down with a heat exchanger with a secondary cooling circuit, which flows with water. A common thing for all our products is that they are compatible with most hardware vendors, and this solution is also ready for Tier 3 and Tier 4 compatible. This is for any data center that may require more safety or any requirement that requires redundancy. This solution is ready for it. For the MicroPod, which can dissipate up to 7 kilowatts, is the more versatile unit. And its main characteristic is its capability of running in outdoor operating conditions, bringing the user closer to the computation spot. So this unit is preferred for edge computing applications. And this is what we call a data center in a box, since all the equipment is already integrated in the device itself. Here we can see some of the benefits of our solutions. And the first one that I would like to mention is this unrivaled total cost of ownership, mainly thanks to the very low operational and capital expenditures they offer, as well as the huge amount of computing density it can offer compared to a typical data center. As well as increasing efficiency, our solutions also help to increase sustainability, as you can see on screen. And with our solutions, we are able to capture 99% of heat and zero waste of water. Then, what is Submer Smart Coolant? Submer Smart Coolant is a hydrocarbon synthetic fluid which we develop in-house, and of course it is ready for working with all the electronic devices. And one of its main properties is that it is dielectric. That means that it conducts heat, but it does not conduct electricity, of course. And the most important properties, apart from being dielectric, are, for example, the lifespan of this solution, which we have proved to be 15 years, and the non-corrosiveness, oxidativeness, and of course, any fluid loss during the operation of our products. And this is a very important thing in a data center. Of course, it also protects the IT hardware against dust and moisture. And well, it is environmentally and people-friendly since it's non-toxic, biodegradable, and not flammable. As I mentioned before, all these solutions are compatible with major hardware vendors, starting from NVIDIA, Fujitsu, Lenovo, Intel, you say it. There are lots of them, and we are compatible with these vendors. As you can see from this map, we're already in a number of data centers around the world, and we move from hyperscalers to hypercomputing centers, co-location, and also telecommunication centers all around the world. And here we will now start talking about where SimScale plays its main role. And it is in the part of developing our thermal solutions. So in our design process, we always start by analyzing and carrying out theoretical and first principle approaches, which we then always validate with CFD, computational fluid dynamics, since some of these calculations are very difficult to carry out with very good accuracy. So we need to go to a numerical analysis, and afterwards we validate these simulations with testing and post-analysis. So SimScale helps us developing our solutions during this process. And well, why SimScale? Basically, because we don't need any hardware in order to carry out the task. We have the typical office laptops, and these are enough to run any simulation independently on how large your mesh is or whatever it is you want to simulate. As Victor mentioned before, the complete parallel computing solution is also very interesting. You don't need to wait for a simulation to be completed. And this is very valuable since we need results and we need them fast. Also, we have a complete package. This is, you don't need to have a CFD package and then ask for multi-phase a library or a finite element method package. It's everything included in the platform, which also contains post-processing tools, which are very powerful. And last but not least, I think this is very, very, very important. They always have helped us during the learning process of using SimScale, and also during all the design process within the CFD simulations, because there are always doubts and technical things which we don't know, and Victor and the other people from SimScale are always willing to help us. So some examples of what we do here with SimScale, and it's important to remind that these are multi-domain simulations. So we do not always carry out the typical CFD simulation in order to see the fluid flow. We have also used multi-phase simulation in order to check the fluid flow in one part of the SmartPod tank. and also structural analysis with the finite element method. So, for example, this an example of a runs simulation. It's been a sensor calibration. In our devices, we have plenty of sensors in order to make sure everything is going right, and it is very important to see if these sensors measure correctly. And one of the things that our SmartPod, the smart coolant shows is that the thermophysical properties vary with temperature, and it is important to see how these thermophysical properties affect on the measurement and also the position of the tip of the sensors. So this helped us understanding that the jet on the sensor tip was important, and it also helped us modifying some specific parameters of the sensors in order to properly measure the fluid flow. And regarding the thermal part, one good example was this one about stratification and fluid flow. This study was mainly a conceptual one in order for us to understand how different possibilities of fluid inlet in our distributor parts may affect the overall stratification of the tank. And as you can see here, we have lots of configurations with different inlets directions, positions, also the outlets were modified. And this was the first part of the design where we didn't have anything but just the tank and the smart coolant. And it helped us analyzing which solution or configuration led to the smaller tank stratification. Later on, by increasing the difficulty, let's say, or the complexity of the simulation, we introduced a fake server with some devices, heat devices representing the CPUs or GPUs of a server. And the same study was carried out, but in this case with the best previous solutions that we found out. And the same thing, we wanted to check how it affected the overall temperatures in these heating devices. And yeah, we grabbed some numbers here in order to say, okay, this solution might be better. Maybe we consider that for different designs, different possibilities. It also helped us checking the fluid flow, which is very important in immersion cooling because it is not the same having all the CPUs and GPUs in series, one on top of the other. And it was interesting to see how the fluid flow affected these let's say very warm flows around the tank and around the server. So yeah, that's how SimScale has helped us, among other things, to develop our products. So thank you so much for being here. If you want to receive more updates or wanted to know more about Submer, you can visit us on our website, submer.com, or following on our social media in LinkedIn, Facebook, Twitter, Instagram, and also on YouTube. So thank you.
Thank you, Luis. Very informative. So now on to the question and answers portion of the webinar. So I will be taking a peek through the questions and questions chat. If you have any, please feel free to pop them in there as we go along. So I've already got a couple here. First one would be for you, Luis. So how was the learning curve with the SimScale platform?
For me, I already did lots of CFD with other packages, but it was pretty straightforward to get into the platform. But I think that was mainly due to the technical support. So knowing the typical process of a CFD simulation, which is pre-processing, meshing, and then calculating and post-processing, taking the detail into every one of these aspects, it was very, very, very helpful to have the technical team.
Understood. Okay, thank you. Next up, so for you, how important would you say simulation is in general in your overall design process? You gave us a little bit of a peek into that, but yeah, how often are you using this, for example?
In our case, it is kind of crucial to carry out a simulation before going to the testing phase of any idea or prototype. Since the hand calculations and first principles approach are not enough, so we use them like on a daily basis. Yeah.
Okay. Another one here. So this one, I think, more from my side. What is the best way to start a simulation project for a data center? So, good question. On that one, I would say it depends. Like any CFD or just simulation in general, right? It depends on what the question is exactly. First thing I would do is I would define the scope. So, depends on the range. If we're looking at a simulation of a SmartPod, for example, that's a pretty different scope than a simulation of a a data center cooling center or with multiple racks and hot aisles and cold aisles, etc. So I would start off by defining the scope, figuring out what exactly it is I need to know to answer my problem of the day, whether it's I'm trying to get a single component down and cool in heat, or maybe, for example, one of my cooling racks has failed and now I only have 4 out of the 5. Is the data center sustainable? Will I start to lose servers, etc.? And based off of that scope, I will start plugging away, making my assumptions as needed, trying to keep it as simple as possible while still answering my base question in the end of the day.
Luis, it's Nagman here. Thank you so much for that fantastic presentation, and likewise, Victor, for taking some questions. Luis, we have a couple of questions coming in for both of you. Let's try and get through a few of these. I guess the first one, Victor, for you is, what kind of CAD models and geometries can a SimScale platform handle in terms of importing and working with?
That's a good question. We support a variety. So SolidWorks, CATIA, plenty of different native files that you can drag and drop into the platform itself. Failing if we don't support native, you can always bring in something like a step file, which is a fairly generic CAD format that any competent CAD tool should be able to export for you.
Okay, great. Thank you. Luis, we have a question for you about the Submer products in terms of how are the wires, the wiring in and out of your products handled?
This depends on the type of server you are using, but most of them you take all the wiring out to what we call the dry zone. Yeah, we take out all the Ethernet cables, all the PDU connections. We have that outside the tank, and it is managed from the outside, pretty easy. Yeah.
Okay, fantastic. A question maybe for both of you here. A question from Gabby is, what pressure ranges would your software be able to work within? If we have a tank with 30 bar pressure, and we have pressure differential in that tank with heat flow as well, is the tool able to operate in that range? And what advice would you give? Victor, maybe, yeah.
Yeah, I can grab that one. So, I mean, I guess that's maybe a loaded question. It depends on what the fluid is, first of all. So assuming it's a liquid, there's really not much of a limit in terms of how much of a pressure we can handle. As liquids being incompressible, it's only relative pressure differentials that matter. If in terms of a gas, similar case there, but now it's going to depend. So long as flow is subsonic, really is the main limit. So if you don't expect flow to exceed the sonic barrier, we should be pretty comfortably able to handle it.
Okay, fantastic. Likewise, Gabby, if you have any other questions, or you have a project in mind, you want a quick chat with us one-to-one, we can take a look at it, discuss where SimScale might be able to fit in as well. A couple of other questions here. So we're talking about the main benefits of simulation. These are 2 or 3 questions combined actually into one, Lewis. So data centers, obviously you can't, these are big products, and each large data center is a bit different in terms of its design, right? You can't do kind of physical prototyping or other things. How critical is simulation to really optimizing the sustainability and energy efficiency and performance of data centers? Especially moving forward, you see a lot of issues with power supply, energy efficiency targets, carbon emissions, extreme weather, and also obviously the demand exploding as well for data centers.
So you said how these simulations can help us approaching these values?
Yes, I mean, how important would you say simulation is in general to the future of data center design? With all your sustainability, energy efficiency, carbon emissions targets,
Yeah.
Everyone's trying to make more energy efficient net zero data centers, right? And there's more demand, right? The demand for data centers is growing. How important is simulation in general, would you say, to this whole industry?
These CFD simulations, I mean, they can be used for almost anything you can think of. And these are not, I mean, this can also be used not only for simulating the behavior of a fluid inside a tank, but also to simulate the behavior of a whole data center, which is also very important. Nowadays, most data centers are based on the typical solution with air, and this leads to very warm data centers, which leads to very low efficiencies in these places. So this is one aspect that where when CFD simulations can help analyzing, checking this out, also including the environmental factors such as temperature, radiation also. So yeah, it will be necessary, of course.
Fantastic. We've also had other customers who are simulating data centers model the external environment, Lewis. So, for example, positioning of ventilation grills around the data center in terms of building aerodynamics to avoid re-entrainment. If you have exhaust gases from, let's say, a diesel generator, you don't want that going into the supply intakes of of the building. So I think that external side is a whole nother conversation, right? It's a whole nother topic that we could explore in a separate session. Fantastic. I think what we'll do is let's finish there. This has been a very exciting session. It's time to roll up your sleeves. So if you want to get started with simulations yourself, you can request a one-on-one demo from our website or contact sales@simscale.com, and we'll be in touch with you to arrange a session, and we can take it from there. I'd like to thank you, huge thank you to Luis from Submer. Thank you so much for sharing your expertise and your knowledge and all the hard work you've been doing. Is really exciting and eye-opening for us to see the range of applications you're applying simulation in. And it's good to see you're doing more than just simple flow. So that was fantastic. Thank you, and for all our attendees as well. So thank you, Luis, and to Submer as well for joining us today.
You're welcome.
And thank you to my colleague Victor as well for the live demo of the SimScale platform. Thank you, Victor.
My pleasure.
Fantastic. We'll be in touch, and we'll send a copy, a video of this this session to you as well. And in that, you'll have some links as well if you want to get started and contact us. Thank you for joining us, and have a good day.